make sure that everything is in. Okay, so this is the very first lecture on multivariable calculus. The first topic that you have to know is vectors. What about vectors? Right, so what's a vector? Vector is something that has direction and magnitude. Vector. Direction and magnitude. Okay. So you probably have seen vectors in physics, especially when people talk about the force. So if you have a block and two people are pulling it in two different directions, and let's say one person is pulling it by 5 newtons and the other person is pulling by 5 newtons. The number 5 only talks about how hard these two people are pulling. But these two vectors are different because they are pointing to different directions. Okay? So if you call this V1, and for vectors, people use the arrow notation like that. You put an arrow on top. This one, V2. These two vectors, V1 and V2, are not the same because their magnitude, because their directions do not agree, while their magnitude are equal. The symbol for magnitude is this double line. And in many cases, in physics books, they would use just V1 by itself and V2 by itself for the magnitude. So another way to say that their magnitudes match will be like this. So these are both magnitudes. Because they both have 5 as the magnitude. Now, in the textbook, people will use boldface letters to denote vectors too. So there are two notations for vectors. So two notations. Vectors. So one is arrow. So you have V on top. And another one is boldface. So the letter is written as V, but with boldface. So it's thicker. Now, now the problem with this boldface is that if I start using the boldface notation, then I'll be basically coloring the board every minute or so. So that's not convenient, right? So because of this, when boldface letters are written on the board, some mathematics teachers develop this something called blackboard bold. Blackboard boldface means simply you have a V and you put an extra double on the last one. So that would be blackboard bold. So if you had the vector u, for example, this will be all vector u. U with an arrow, or u boldface, or u blackboard bold. Now, textbooks don't need blackboard bold, so you're not going to see this in most books. Some older books, I think they use this. So you'll be mostly seeing this, but in my lectures, a lot of times I'll be using the blackboard bolt, especially when it comes to something called standard unit vectors. I'll explain that later. Okay? So in my class, I'll be mostly using this one, but sometimes using the blackboard bolt space. And then for the magnitude, we have two different notations where no decorations are given, or you take the vector and you put double lines left and right of it. And again, because this one will be hard to distinguish with the boldface, I will try to use the magnitude notation as much as possible. But this is something to keep in mind, especially I know that a lot of people are taking Physics 1 or 2 with my class, Multivariable Calculus. And when you read the physics textbooks, if you don't have the knowledge that these things mean scalars, magnitude, scalars, and those mean vectors, then you get really confused at what you're reading. Okay, so it's very important to distinguish between the two. All right, I wrote scalars without explaining what this is. Scalars just means it's not a vector. Okay? Any number that's not a vector, the regular numbers that we usually use, those are called scalars. All right. Okay, so we have this. Now, vectors were first used by Newton because he wanted to explain how to add forces when they're not aligned together. See, if you have two forces acting on this with certain angle here, let's just say this is, I'll just say this is 60 degrees. Doesn't look 60 degrees. Let's just say that's 60 degrees. Okay, in that case, what is the sum of these two vectors? Well, the way you add vectors is by using a parallelogram. Okay, so you draw this imaginary parallelogram, and you draw this third vector, and that's called the sum of the two vectors v1 and v2. So, I have to say, addition of vectors is there are two ways to add vectors. Number one, parallelogram rule. Which is, if you have one vector, another vector, let's say this is u and that's v, then you do this parallelogram, and then you connect the initial and terminal points of the of this. You use these two vertices to make the initial and terminal points of the vector. That's called the parallelogram. And then secondly, there's the triangular law. Which is, so if you had a vector here and a vector there, u and v, then you move this vector u over here, and you draw this triangle. Now, while explaining this, I just realized that I forgot to mention something that's important. Because I'm saying that a vector is a quantity with a direction and magnitude, and it doesn't say anything about where it's applied. When we talk about vectors, we identify two vectors of the same magnitude and direction regardless of where the vector is at. Okay. So whether you have this vector here or there, as long as they're pointing to the same direction and they have the same magnitude, we say this vector is same as this vector. So this is also thought as u. So that's something to know. Okay. The reason for identifying has to do with physics, because I mean, if you're trying to move some object and you're pulling it this way, that's same as pushing it from here, right? So a vector that's applied here or applied there, it's the same thing. So when you try to apply vectors to forces and a lot of different things, often the point where it's acting on is not very important. You should be free to move it around. So that's why vectors are identified even if they have different initial points. All right, so this one I'm saying, the triangular law goes like this. You have a vector, you move it to another place so that the initial point of the first vector is at the terminal point of the second vector. So now you can connect the two vectors, right? If you connect the two vectors, then connecting the initial point of the second vector to the terminal point of the first vector gives you a new vector, and that's called the sum of two vectors, u plus v. So in this picture, I have u plus v. I have another way to add two vectors. Yeah, and there, as you can see in the picture, I didn't draw them in the same way, but if I drew this exactly like this one, you'll see that it's referring to the same line. So whether you use a parallelogram law to add two vectors or a triangular law to add vectors, it doesn't matter. All right, so those that's the physical understanding of vectors. Now let's move on to mathematical understanding of vectors by putting these vectors into the coordinate system. So vectors in coordinate system. Okay. Let's first think about two-dimensional vectors. Sometimes you can describe a physical phenomena limited to just two dimensions. You don't require this extra dimension. And in such a case, you can put the vector on the two-dimensional Cartesian plane, the rectangular coordinate system, where this is x, that's y. And let's think about 2 points. Let's say this is P, and P is A comma B. And let's call this point Q, which is C comma D. And let's think about the vector PQ. So I'm thinking about a vector that starts at P and ends at Q. Now this vector can be written by the following way: PQ with an arrow on top. So that means its initial point is P, and its terminal point is Q. Okay. Now, there are some special class of vectors. I can't say special class of vectors. Okay, so let's talk about the origin. Now we can use this terminology using the origin. Origin is this specified point on the coordinate system where x and y coordinates are 0. And in that coordinate system, we can talk about the vector OP and vector OQ. This vector will be OP, that vector will be OQ. Right? When the initial point is at the origin, we have a special notation for the vector OP. The vector OP, rather than saying it's a vector starting at the origin and ends at AB, if it starts at the origin, you only need to be concerned about the terminal point, right? So the terminal point is all you write. So you write A comma B with this angled bracket. So whenever you see this angled bracket with two numbers, you should understand it as, oh, it's a vector whose initial point is at O, and its terminal point is at the point A comma B. Does that make sense? Okay. And OQ should be written as what? C comma D. This angled bracket. All right. Now, for those of you who usually learned only the parallelogram law and did not care much about the triangular law, this is a good time to see the value of the triangular law, because you see here that this is OP, that's PQ, and if you add OP plus PQ using the triangular law, what's the result?
OQ.
OQ, right? So we have the following property that triangular law implies of vector addition implies that OP plus PQ is equal to OQ. And this equation will be often used in the following form. I'm going to subtract OP both sides and write down PQ is OQ minus OP. In other words, since OP is A comma B, and C comma D is, OQ is CD, CD, and OP is A comma B, this will be the formula that we use to find the vector PQ. Now, often I will abuse the notation. So rather than writing down CD with angled brackets, I'll just write down C comma D parentheses A comma B. I'll just write it like that, but you should just understand this as subtracting two vectors. In fact, many books just take A comma B with the regular parentheses and treat vectors like, oh, it's just points where you have additions between points. All right. So this is the formula, and I'll even write it in the following way. I'll just say that if you want to find the actual number for PQ, what you do is you do terminal minus initial. And the reason I say that is because after all, C comma D is Q, which is the terminal point of the vector, and P, which is A comma B, is the initial point. So I'll often say PQ is terminal minus initial. Okay, so let me try to explain how we use that by an example. So here's an example. So here's a 1, 2. And here's 4, 1. And let's just say this is P and that's Q. So what is the vector PQ? Now let's think about what this question means. In other words, I want you to express this vector by this notation, the angle bracket notation. The angle bracket notation, as I explained before, you can think of it as a vector that starts at the initial, at the origin. So you can move this parallelly to over here and think about it like something like this. So we actually know the answer already, right? According to this picture, what's this vector? It's right 3 and goes down by 1, so this is 3, -1. And since it's connecting the origin to 3, -1, it must be 3, -1 with the angle brackets, right? So that's something that we can find graphically, but often this is not so easy, trying to draw the graph exactly and trying to find the coordinates exactly. It doesn't work, it's not very convenient. So rather than drawing the graph to figure out what PQ is, the standard solution I would like to promote is using the terminal minus initial. So let's try this solution. Terminal is, so PQ is terminal minus initial, so what's the terminal? 4, 1. Remember, I really mean 4, 1 as angle brackets, but I don't care, okay? So let's write 4, 1 minus 1, 2. Right? And then what you do is you compute this coordinate-wise. So you do 4 minus 1, which is 3, 1 minus 2, which is -1. Hey, it's the same thing, right? And you put angle brackets. That's what I mean. Okay. Now, vector addition in 2D. If you have a vector A, B, and C, D, adding just means it's a coordinate-wise addition. Okay. And in fact, that's what I have done here. It's a coordinate-wise subtraction. I should probably have explained this first before doing that, but I kind of jumped ahead. All right. And then scalar multiplication is if you have a constant C multiplied to A, B, you multiply this to individual ones. So those are what you can do with vectors in 2D. Now these two operations can be done without really having a coordinate system. We already showed how, we've already seen how you add vectors. You can use parallelograms or triangle to add vectors, right? So really, if you're, after defining vector addition like that, you should really check if the two different definitions agree. And it does, okay? I'll skip the proof. Why adding coordinate-wise is the same thing as actually drawing a parallelogram and doing that process. Yeah, I'll skip that. It's not that interesting, but if you are curious to know, just try to draw. I mean, for example, try to see what you get if you add 1, 2, 4, 1, and put that third vector here, and see if they form a parallelogram. You will see that they do form a parallelogram. Okay. So that's something that you have to check. Scalar multiplication too. This just means that you're resizing. If you put a 2, what does that mean? You have a vector and you double it. That means the magnitude is doubled. The direction stays the same. Okay? So that's how you can define scalar multiplication without having to write the formula. Graphically, it just means you're rescaling the magnitude without changing the direction. Of course, if c is negative, that means that the direction will be the opposite. Okay. Okay. So those are the two operations. And then the magnitude of a vector is if you have a comma b. Now let's think about this. You have a comma b here, and because of this angled bracket, that means that you're connecting it to the origin and you're trying to find this length. Well, we already know how to find this length. You just use Pythagorean theorem, right? A squared plus b squared gives you the length of this squared, right? So you take the square root of what? Square root of a squared plus b squared. So that's how you handle vectors in 2D. Okay, what about 3D? It's the exact same thing. In 3D, you have scalar multiplication, vector addition, magnitude, and all that. Okay, so in 3D, again, ABC plus DEF is A plus D, B plus E, C plus F, and if you have some K times ABC, you just multiply to each individual ones. And then if you want to have the magnitude, you square all the components, add them together, and take the square root. So you can see how they correspond. Do I have to explain to you what 3D coordinate system is? You just have an extra z component, right? So you have x, y, and z. So a vector in 3D will be like, if it's like 1, 2, 1, what you do is you go forward 1 step, 2 to the left, and you go up by 1 step, and connect it to the origin, and that's the new vector. Okay. So you can talk about vectors in 3-dimensional space.